So it's another one of our videos looking at June 2018 paper 1 for iGCSE Edexcel 9 to 1. So it's an exam question for 5B solid liquids and gases and section 2C electricity potential difference. So quick show of the equations. You can pause that, have a think about what you would need and what you need to learn. So a student has a small piece of steel, describes an experiment you could do to find the density. You can use a diagram to help you out. There are 6 marking points actually, but you only get 5 marks. And they're really simple stuff, so measure, find a mass, using a balance, allow scales, measure, find the volume. Using a displacement method, so we're thinking of a eureka can, so you put the rock in and the water comes out, that kind of thing, or the steel. Particularly, it tends to be steel is rectangular, so you normally have just weigh it, but if you're using an irregular shape, the displacement can is definitely superior. You could talk about a precaution, so the object tied to a thread so it doesn't fall in. Be aware of the meniscus, the curvy part, measuring at eye level, repeating readings, taking an average, zero the balance. There's loads of them. Balance on a horizontal surface, don't splash the water, someone might slip, measure the mass before the volume. And then you want to say use the formula, so density formula, mass over volume, must be in that form. So it's quite straightforward for a wordy bit. They would allow symbols as well. So student investigates how the length of a piece of wire affects its resistance. Photograph shows, here we've got our piece of wire, and we're going to measure the length of the ruler. State how we could improve the precision. Now, this is where a lot of people come unstuck. The second question, if you read ahead, think about your exam technique. This suggests 3 ways in which you could improve the accuracy, so they're clearly wanting you to look at the difference between the two. And it's not as easy as it looks. I'm going to put both answers up at the same time so we can compare. So, first part then, if you used a half scale or millimetre scale, that would help you with the random errors. It's actually a better idea to repeat the readings, is actually better because it reduces the impact of the random error. You can't get rid of the random error. And also we should think about the precision that it's actually no indication of how close we are to the true value. So we could be fairly precise, so get the wrong answer many times over and not be as accurate as we wanted. So the 1 mark for that part, 3 marks for the second. They don't want anything about repeating or averaging because that helps with the precision. And a measurement of this result is considered accurate if it's judged to be close to the true value. So we're looking at marking point 1, parallax error, something like that. Place where the wire is, where you're measuring it. Straightening the wire, it looks pretty crooked. Start the measurement from an integer on the ruler or 0. So you could actually push it right to the end of the ruler and have a little guide to stop it from having an error there. And you could make sure the ruler's parallel. That would be another one. So relatively straightforward if you know the difference between the two. You've got to factually learn that though. Now the student tries to find the resistance for 7 different lengths. He does this by passing a small current through each wire. Explain why the current in each wire must be small. Relatively straightforward, this one I think. Reference the temperature of the wire changing, i.e. it gets hot, it melts, nothing to do with any control variables in there. Preventing an increase in resistance due to heating, and anything that's incorrect would negate from the stuff you've put, so you're best off not writing too much. 5B part 2. The table shows the student's results, so we've got length of the wire in centimetres, resistance in ohms, no symbol used, just ohms. Okay, 2 improvements a student could make to the data he collects. Well, very simple, extend the range of length. So we could use a bigger range, so maybe 5 to a metre, or 0 to a metre to see what happens. Filling gap in results, so if there's gaps, so i.e. 10, 15, 20, there's nothing between 20 and 50. It's not a lot of good, is it? It's not good. You could take repeats and average, so take the resistance 3 times and then repeat and check for anomalies. That, like we said, feeds into our idea about improving our precision. You could take results at smaller intervals, so you could go every 5 centimetres. And here you've done some at 5 and some not, or every centimetre, that would help. So easy improvements. And then the last part of this one is plot a graph of the student's results on the grid. Then draw a line of best fit and then describe the relationship. Well, this is what the example thought we should do. Simple sort of line graph with our data point C. I don't think his or her crosses are that big. Personally, I draw slightly bigger crosses. The scale should be 50% at least on both axes, and in this case it takes up most of the space. Linear label on both axes, that's correct, so you're just transposing what was on the original question. I mean, that's very simple, and the units are there. How can you go wrong? Plotting tolerance within a little square at least, so between plus or minus half a square. Okay, if you're not within that square, you're going to get a mark dropped. Okay, so for each time you drop it, you lose a mark, and obviously if you plotted them all, you start with 2 and then it disappears. Suitable straight line of best fit, no more than 1 square from any point, so it's really quite tight data. It's quite close to the true value of this data, so there's not much margin for error. It's gone through the origin. And the relationship, simple pattern. As length increases, resistance increases. The second mark is if you say proportional. Some people talk about directly proportional. There's no such thing as directly proportional. You're either proportional and you go through 0, 0, or you're not. But some language and examiners seem to bring in this direct bit. It's meaningless. And the other point is, what's a positive correlation? Maybe useful in maths, in physics we never use it, so please try and avoid it. So there we go, that's our review of that question. Hope you enjoyed it.